Hello, in this chapter we're going to be discussing acids and bases. Some of the more important learning objectives include defining Bronsted-Lowry acids and bases, as well as conjugated acids and bases, applying the curve error representation we saw in the last chapter to show flow of electrons in acid-base reactions, using pKa values for comparison of acidity and basicity, as well as comparing acidity and basicity based on a number of factors such as structural, including conjugate base stability, and a comparison of the stability of negative and positive charges. Predict equilibrium position of a reaction based on a comparison of the conjugated acids and bases. Explain the significance of leveling and solvating effect, and differentiating between Lewis acids and bases and Bronsted acids and bases. Lastly, describe the purposes of carboxylic acids and amines in amino acids, and identify the sweeter ionic form of an amino acid. Recalling from our general chemistry, the Bronsted-Lowry definition of an acid is a species that donates a proton, and a base is a species that accepts a proton. We have a classic example here on the bottom. We have hydrochloric acid, and you can see highlighted in red that proton that can be donated, and water, which acts as a base, meaning that it will accept that proton. In this scenario, because hydrochloric acid acts as the acid, its analog on the right side or the product side of the equation would be the conjugated base right here, and because water will be accepting that proton, here it acts as a base, but then on the right side it becomes a conjugated acid. By the Bronsted-Lowry definition, a conjugate acid results when a base accepts a proton, just like we mentioned in the past slide, and a conjugated base results when an acid gives us a proton. In here, we have the species that has a negative charge. We have the proton again highlighted in red. This species, if you compare left to right side, it accepted a proton, so this will be a base and its conjugated acid. Therefore, this will be the acid and its conjugated base. One thing that we do in organic chemistry is that we take advantage of the arrow or curve arrow notation to describe acid-base reactions in terms of electron flow or electron movement. We use arrows to describe the flow of electron density. You can see here, for instance, the base is using a lone pair of electrons to sort of bind to that proton that it will be accepting, and the two electrons here in this bond are going to move straight to what will eventually become the conjugated base, and this will be the result of that acid-base reaction. As you may have noticed, these are the same arrows that we use to draw resonance structures. So as you can see, this curve arrow system or model will be applied to a variety of scenarios. It's important that you familiarize yourself with how to use these curved arrows, because you will see a lot of them moving forward. Looking at this specific example, we can say that the base is attacking the acid using a pair of electrons. Rather than saying that the proton is moving, we say that the electrons are moving towards the proton. The acid cannot lose its proton without the base taking it. All acid-base reactions happen in one step. The mechanism that we're seeing here shows two arrows indicating that two pairs of electrons move simultaneously. One shows this is a bond that is being formed. This is a bond that is breaking. From general chemistry, we were able to tell differences between strong and weak acids and bases. So one measure that we use for strength of acidity would be pH, which for more generic species we use pKa, pKb, and we combine them to do pKw, all that stuff. So now we're going to be applying a little bit of that towards organic reactions, acid-base neutralizations. The strength of an acid or base is helpful to predict how reactions will progress. Quantitatively, we can use pKa. Qualitatively, we can use such a structural analysis. We look at how stable a structure is before a reactant and then after, and that will tell us a little bit about its reactivity. Looking at it from a purely numerical perspective, we can tell the relative strength of an acid by looking at those pK values. The pK values comes from the Ka, or that constant of acid dissociation once they reach equilibrium. As an example, we have a generic acid-base reaction here. You have your acid, your base, etc. And as you know from your general chemistry, we put the concentration of our products over the concentration of our reactants. Water is not included, so we use for the Ka. So it will be concentration of H3O plus, A minus over HA. Now here, the question becomes, how do I interpret this data? Will Ka being bigger than 1 or smaller than 1, what does it represent? Is it a strong or is it a weak species? For that, because we deal with so small numbers, we're better off using the negative log of Ka, which then turns into the pKa scale. In which case, when you have a lower pKa value, that means that you have a stronger acid. So we're looking at these numbers. The higher they go, the weaker the species becomes. We have a couple of numbers of pKa here that are good for comparison. We have a -9 for hydrobromic acid, and for the ammonium ion, a 9.3. So as you can see, this is a very large range, right? This is a logarithmic scale, so orders of magnitude. Each pKa unit represents an order of magnitude or a power of 10. And we have here a few examples. HBr, hydrobromic acid, 10 times stronger than hydrochloric acid. So we have these two right here simply because there is a difference of 1. That means that it's 10 times stronger. You can also use pK values to compare the strength of bases because usually the stronger the acid, that means that the conjugated base will be weaker, right? That's sort of an inverse relationship. If you think about it, the stronger the acid, that means that it is very willing, or it's very likely that it'll give up a proton. And if it gives up a proton very easily, it is not very likely that it will accept a proton, therefore making for a weak or an unfavorable base. So that's that inverse relationship that we like to see with acids and bases. With the relevant pK values, we can now start comparing apples to apples. We can predict which direction an acid-base equilibrium will favor. Higher pK means that we have a weaker acid, like we just saw a couple of slides ago. So here, for example, we're comparing this acid, which is water, to this other acid, which is terbutyl alcohol, pK of 14 versus pK of 18. In this case, this reaction demonstrates what is always true in an acid-base reaction. Equilibrium will favor the weaker acid and the weaker base. So what that means is that these two species right here are going to react to a rather large extent simply because the acid that you get on the product side is much weaker. Subtracting the pK values also tells you that there will be 10 to the 36 times more product than reactants, at least for this specific example. We're no longer talking about the one on the last slide. 14 versus pK of 50. Like pK of 50, ridiculously weak, versus something that is much stronger by comparison. Thinking about this, pKa is a logarithmic scale, so every number, order of magnitude, so 10 to the 36, that's where that comes from. In this case, because it's 10 to the 36, that is a rather large number, we can even go as far as saying that there won't really be an equilibrium. It's more of an irreversible process. There's no way that you can go from a pK 50 to a pK 14, right? That reverse reaction. To determine the relative strength of two acids, without knowing their pK values, we can compare the stability of their conjugated bases. The stronger the acid, the more stable its conjugated base. When an acid loses a proton, it forms the conjugated base, which has a lone pair of electrons that resulted from the loss of that proton, that H+. To determine the stability of a conjugated base, we are looking at the stability of the lone pair. The more effectively a conjugated base can stabilize its negative charge, in other words, the lone pair, that means that the acid will be much more likely to deprotonate. In other words, you have a stronger acid. There are a number of factors that affect the stability of a negative charge. We have the four main ones here. The first one is going to be the type of atom that carries a charge. The second will be resonance effects. The other one will be inductive effects. And lastly, the type of orbital where the charge resides. These factors can be remembered with the acronym ARIO.